All right, so we have the practical exam question. It's a very simple question. The question says, assuming that you used 4 ml of benzoyl chloride and 10 ml of 0.88 molar ammonia solution, calculate the percentage purity of benzamine, assuming the actual yield is 2.5. Now, the yield you got at the end of your practical is 2.5. So we come here and write it down. First of all, let's write the equation of reaction. So you come here and write equation of reaction. This is the approach you should take for the exam. So you have benzoyl chloride, which is of course something like this. Right? React it with 2 mole of ammonia. This gave us benzamide. So you got something like this. You write the equation of reaction again. C double bond O NH2 plus ammonium chloride. Right? Now, you're now going to write out your parameters. Come here. Actual yield. What was the actual yield? I think 2.4. Okay, 2.5. Sorry, 2.5. What other parameter were you given? Specific gravity for benzoyl chloride. Was given as, think, 1.22 gram per mil. So you have 1.22 gram per mil, right? Exactly. Now the question now is calculate the percentage, the percentage purity, right? Now what is the formula for percentage purity? Percentage purity, let's write the formula first, is equals to actual yield all over theoretical yield times 100%. That's percentage purity. What other thing were you giving? We are giving the masses of each of them. And then we are giving 4 ml of benzoyl chloride. So you can come here and say volume of benzoyl chloride. Volume of benzoyl chloride equals to 4 ml. Right? Exactly. Equals to how many mil? 4 mil. Now you don't need any information concerning ammonia for now. Is that okay? You don't need any information concerning ammonia for now. Now let's look at this. It's very easy. Now what is specific gravity? Still the same thing as what? Density. Right? So we can say density, which is the same thing as specific gravity, is mass all over volume. Are you getting it? Then we can cross multiply because we must look for the mass. We can now say that the mass is equals to density times volume. Right? Now what was this? The mass of benzoyl chloride now, because the specific gravity was given to you, which is the density. You can use that to calculate the mass of benzoyl chloride instead of using volume. The density was 1.22 gram per mil times the volume is 4 mil. This mole can cancel this mole. Our mass of benzoyl chloride that is contained in that 4 mole. Mass of benzoyl chloride contained in 4 mole would be equals to. Now, we need to look for the mass of benzoyl chloride because we are going to use it later to work. Alright? So let's punch our calculator and see what that gives to us. This will be 1.22 times 4, which is 4.88 gram. Alright? So the mass of benzoyl chloride used is 4.88 gram. Now see the equation of reaction. The mole ratios for this we have here is benzoyl chloride. The mole ratio for benzoyl chloride to benzamide is 1:1. So this is the benzamide you are looking for. Now since the mole ratio is 1:1, it means 1 mole of this gave 1 mole of benzamide. You are now going to come here and write 1 mole of benzoyl chloride, my dear students, is equals to 1 mole of benzamide. Now, what is the mass of 1 mole of benzoyl chloride? That's another thing you need to know. So you now say 1 mole of benzoyl chloride is equals to the mass, which is equals to benzoyl chloride is, what is the, no, I don't need this. What is the molecular formula of benzoyl chloride? From what we can see here, we can see benzoyl chloride is C. How many carbons are here? 1, 2, 3, 4, 5, 6. Plus this one here, making it C7H. How many hydrogens do we have? 1, 2, 3, 4, 5. C7H5. Are you getting it? Then 1, 2, 3, 4, 5. Then OCl. So benzoyl chloride is C7H5OCl. What about benzamide? Benzamide is C7H. This is 5 from here. Hydrogen 1, 2, 3, 4, 5. Plus these 2 here. H7. And then you have O. C7H7O. So benzoyl chloride C7H5OCl. So let's write it here. C7H5OCl. Now, from atomic mass, carbon has an atomic mass. It will be given to you of 12. 12 times 7. Hydrogen is 1. 1 times 5. Oxygen is 16, which is 16. Chlorine is 35.5. So 1 mole of benzoyl chloride, what is the mass? To be 12 times 7 plus 1 times 5 plus 16 plus 35.5. In this case, it's giving me carbon 12. Yeah, 12 times 7 plus 5 plus 140.5. So we have 140.5 gram. So it means 1 mole of benzoyl chloride has a mass of 140.5 gram. Is that okay? Now, what about 1 mole of benzamide? What is the mass? So you now have 1 mole of benzamide, right, is equals to C7H7O. And there you have N also. I didn't indicate the N here because you have a nitrogen atom, right? I have a nitrogen atom, so we are supposed to have N here. All right, so we come here and also indicate that. So calculate. This will be 12 times 7 plus 1 times 7 plus 14, plus 16 rather, first, plus 14. 12 times 7 plus 7 plus 16 plus 14. That will give us 121 gram per mole. So this equals to 121 gram per mole. Is that okay? All right, now that you have done this, 1 mole of benzamide gave 1 mole of, 1 mole of benzoic chloride gave 1 mole of benzamide. What was the mass that was given? The amount we calculated, the mass of benzoic chloride that reacted was 4.88 gram. So you already know this relationship, and you know how we calculated the 4.88 gram now. From mass is equals to density times volume. Is that okay? To get the mass of benzoic chloride, because if 1 mole of this is equals to this, that means the mass of benzoic chloride is supposed to give us X gram of benzamide. So we can now come here and say 140.5 gram of benzoic chloride is equals to 121 gram of benzamide. What was the mass of benzoic chloride that we just calculated from the question that was given to us? 1.22 gram is the density times 4 mil, which is 4.88 gram. So you are now going to say 4.88 gram of benzamide will be equals to what? Of benzoic chloride, will be equals to X. Now cross multiply. What are we now going to have? To be 140.5x is equals to 121 times 4.88. Now divide both sides by 140.5. Is that okay? So that at the end of the day, when this cancels this, X will be equals to 121 times 4.88. I'm going to have 121 times 4.88, which is 590.48, divided by 140.5, which is equals to 4.20 gram. So our expected weight is 4.20 gram. That will be our expected weight. Is that okay? 4.20 gram. But what we are having, what we are given in the question right from beginning, that what they got from the practical was what? Actual yield was 2.5. Expected theoretical yield, rather, let me put theoretical yield. Are you getting it? So theoretical yield is supposed to be 4.2. So we come here and say this is theoretical yield. Good. So how do we do this now? To calculate percentage purity, we said percentage purity is equals to actual yield over theoretical yield times 100%, which is equals to actual yield is 2.5, theoretical 4.2 times 100%. When you punch this in your calculator, it's going to give you 2.5 divided by 4.2 times 100, which will give us 59.52% weight by weight. So this is our percentage purity for benzamide. Is that okay? The percentage purity for the benzamide that was used for this practical. Now, the next question here says, explain the procedure required to fully characterize benzamide. Now, this question is a setup. Now, if you want to characterize something, which is number 2, to characterize an organic compound, it means you want to get every detail about that organic compound, including the molecular mass. So 1, to determine the molecular mass of the compound, first of all, you want to determine the purity. To characterize it, you want to determine the purity. The purity, you use melting point, right? And how do you carry out melting point experiment? First of all, you put your sample in a capillary tube, right? Now, how do you characterize using the melting point? You get few samples, usually a small amount, and put it into a capillary tube, right? So you have this inside the capillary tube, and then you take this pure sample, the dried sample. It should be dried, and it should be evenly distributed in this capillary tube, right? And then you take it to the melting point apparatus. Telling you how to characterize now using melting point, the melting point apparatus. Now, after you take it to the melting point apparatus, first of all, record the temperature, the initial temperature of the apparatus, right? Record the initial temperature of the apparatus. Now, then, after that, you will start increasing the temperature at about at the rate of 1 to 2 degrees per minute, right? You increase the temperature at the rate of 1 to 2 degrees per minute. Now, as the temperature rises, let's say the temperature was initially at 25 degrees, then it's now rising to, let's say, 40. As the temperature rises, what you are going to do, observe the sample with a magnifying lens or a microscope, depending on the one that you actually know. Now, note the temperature range at which the substance begins to melt and the temperature at which it completely melts. You know, when something begins to melt, you first of all see liquid. You know it was a solid. Benzamide is a solid. The one you purified is a solid. So note the temperature at which it completely melts. Are you getting it? And then note the temperature range. Now, normally, it's supposed to melt over a narrow range of temperature. If it melts over a narrow range of temperature, it means that it is a pure compound. It's supposed to melt over a narrow range. When we talk about over a narrow range, it means if it starts melting at about 40 degrees, right? At about 41 degree highest, it should have finished melting. But in the situation where it starts melting at 40 degree, at 50 degree, it has not finished melting, it means that there are impurities. Are you getting it now? So that is how you carry out melting point characterization. Now, when we usually talk about characterization, we go beyond melting point. Now, after melting point, the next thing you may do to characterize this compound is mass spec. You can take it to the mass spectrophotometer. The mass spec will tell you the molar mass of the compound, the molecular weight, and the fragmentation pattern of that compound. The molecular weight and the fragmentation pattern of that compound. The next one is you can use infrared spectroscopy, IR spec. Now, what information will IR spec give to you? IR spec will give you information about the functional groups present. Are you getting it now? To give you information about the functional groups present. Then NMRO, you can use NMRO. I'm talking about the characterization, full characterization. What will NMRO give to you? To give you information of the different molecular environment of various nuclei. Different molecular environment of different nuclei. Then you can use X-ray crystallography to give you the three-dimensional this thing. Then also elemental analysis using AAS that we learned today, AAS, UV spectroscopy to tell us the nature of conjugation, and then lastly, thin layer chromatography. It actually to assess the purity and also identify potential impurity. So these are various methods you can use to fully characterize benzamide. Is that okay? So that will be that for this particular one. Okay, that will not be that. I'll come back. My system is low and complete it. All right, we have another question here that says, explain how you will purify benzamide from the reaction mixture. So let us explain how we purify benzamide from the reaction mixture. Now, when you get the reaction mixture, the first thing you need to know is that benzamide will form crystal, right? Benzamide will form crystal in the reaction mixture. Is that okay? So how do you purify this? How do you remove this? First of all, you filter it off, get the crystal. That is filtration to get the crystals. Then you will get hot alcoholic solution. All right, which can be hot methanol or hot ethanol, but most time they use methanol, or a mixture of water and ethanol, which are suitable solvents. Is that okay? You get those things. It should be hot. The reason because the benzamide crystals will often, in most cases, solubilize in the hot alcoholic solution. This is not alcoholic solution. In the hot alcoholic solution. Now, after that, what will happen is that there's something we cool. Is that okay? Now, during the process of cooling, what will happen? It is believed that the impurities will still be solubilized in the alcoholic solution. Is that okay? Let's use methanol for this case. You have, this is the reaction mixture. You have the crystal and impurity. This is the crystals form. And then you have the impurities. Now, it is believed that firstly, when you use the hot alcoholic solution, all these crystals you see here, what will happen to them? All these crystals will actually melt. Are you getting it? They will dissolve in solution. So you are going to form something like this in hot. So this one will be what? Hot. But after some time, when this thing cools down, what will happen is the crystals will reform, but the impurities, every other impurity that were present before, will remain in solution, and then you cannot filter again. By so doing, you've left all the impurities with the alcohol, in this case methanol, and then you get pure crystals. If you are not satisfied, you can recrystallize. Is that okay? You can recrystallize and get your final product. So that is one way to actually get your pure crystals or pure benzamide from the solution. That is this third question. Explain how you purify benzamide from the reaction mixture by recrystallization with what? Aqueous ethanol, or you say methanol, whichever one you use. All right. All right. The next questions are actually spectroscopic questions. Spectroscopy. The next questions say predict the IRO absorption of benzamide. Now, what is the structure of benzamide and how can you predict the IRO absorption? You just predict. You may not really draw the spectrum. All right? Predict the IRO absorption of benzamide. This is benzamide. Now, you write IRO is used to identify functional group. Right? Now, it is a well-known fact that the carbonyl functional group of benzamide will absorb around 1600 to 1700 within this region. Are you getting it now? So you can say that the IRO absorption for the carbonyl functional group will also show at where? At 1600 to what? To 1700. What other functional group do you think? We have a medium absorption. Are you getting it? Broad absorption of NH at around 3000, or let's say 3010 to around this 3050. There will be NH absorption for these functional groups that you actually have here. Is that okay? Which is the NH functional group. And then, of course, we are going to have aromatic ring. This aromatic ring, the CH stretch of the aromatic ring, the CH stretch of the aromatic ring will be around also 1600 for the CH stretch of the aromatic ring. Is that okay? It will also be around 1600. Is that fine? So these centimeter reciprocal, centimeter reciprocal, centimeter reciprocal. So these are the various functional groups that you can actually get from benzamide. Is that okay? So these are just the values you have been taught IRO, so they expect you to actually have a range of these values in your head, but you don't really need to memorize all the values. Just have a range. Like me now, I just picked a range of these values. Is that okay? Then we can have carbon nitrogen. I really do not know where that one absorb, but we can have carbon nitrogen bond that absorb at a particular wavelength. Now, the next question here says, what will be the molecular ion for benzamide? Now, benzamide, when we talk about molecular ion, is actually mass spec. Now, for molecular ion, you write the molecular ion gives us information as to the molecular mass of the compound. So you write the compound in question, all right, exactly. Then you put it in bracket. The molecular ion is formed when an electron is given off. Are you getting it? You actually bombard with high energy electron, which knocks some of the electrons off. So you are going to have a positive charge and what? A radical. So this structure here is the molecular ion of benzamide. Every other fragment can break from here, but for now, this is the molecular ion of benzamide. So any compound that is given to you at all, for instance, if they say what is the molecular ion of chloromethane, all you need to do is put chloromethane in bracket, because the molecular ion we are talking about is when high energy is passed through this. What will happen? It will actually ionize this. So you are going to have a positive charge and what? A radical, because one electron will be knocked off. Are you getting it? So this is the molecular ion. So any compound that is given to you, the molecular ion, draw the compound, put it in bracket, put a positive charge, and then a radical here, because only one electron is actually knocked off. Now the next question says, predict the HNMRO from benzamide. Predict the HNMRO for benzamide. Now, if you are to predict the HNMRO from benzamide, from all we have learned about NMRO spectroscopy, what do you think we can actually do? First of all, we need to look at the various protons in benzamine. This here is the structure of benzamine. All right. Now you have a proton here. You have protons here. You have protons here. You have protons here. You have protons here. Now note something. From what I've taught you so far, you agree with me that this proton and this proton are in the same chemical environment because there's a line of symmetry that actually runs through them. Is that okay? These two protons are in the same chemical environment, so they will have just one signal. This proton here and this proton are in the same chemical environment, so they will have one signal. Also, this proton here is in one chemical environment. And then lastly, the NH proton is also, all right, the NH proton is also in one chemical environment. The NH, we can indicate it with D. So these are the various protons for benzamine that we have. Now, what do you think the structure will be like for benzamine? All right, so we are having this, and the next thing we are going to do now is we have, of course, our 0 point, right? And we have the benzene ring. Now, the benzene ring is usually around the region of 6.5 to 8. So you are going to be seeing all these protons for benzene ring around 6.5 to 8.6. Is that okay? Now, how do we then fathom this out? If we start with A, proton A. Now, you agree with me that for proton A, the neighboring proton, the neighboring carbon, which is these two, they are the same, so they are symmetrical, right? Now, for proton A, the neighboring carbon has one proton here, right? So for each of them, if you want to consider this proton A, neighboring carbon have one proton, so it's going to show as a doublet. Even this one too is going to show as a doublet because it has one proton, and we said if it has one proton, it means n is equals to 1, which is equals to 1 plus 1. So this is going to show as a doublet. Now, how do you represent a doublet? I told you that it will be around the region of what? 6.5 to 8. So let me just come here and put 6.5 here. So it's going to show around this region as a doublet. So you are going to have a doublet here, like this. Is that okay? Now the next one is proton B. Now for proton B, you can say that these two protons are the same. I've explained before. And for each of the protons, you agree with me that they are surrounded with this hydrogen here and this C here. This hydrogen and this one and this. Is that okay? Each of them, proton B, is surrounded with this one and this. So proton B is having two protons, right? And the two protons now would be a triplet. Are you getting it? Because if n is equals to 2, so 2 plus 1 will give us a triplet, which is 3. So you are going to have 3, which is a triplet. Is that okay? So that one now is going to give us something like this. Sorry about that. At around this region too. All right. And then the next one we are going to have now is this C here. Now this C here, depending on the J value from here to here, I've not actually explained what J value is. Depending on the J value from here to here, this C here can actually serve. And then finally, that of C will first of all form a doublet with this B here, and then further splitting with this B, we form a doublet of doublet or a triplet. depending on the J value here, but you don't really need to put such information in your head. That is if at all this thing will come. So we have something like this. This will be a doublet of doublet. I'm going to explain this one later. All right. So this is going to form a doublet of doublet, or in some cases it's going to form a triplet. So this is for C, here is for B, and then finally here is for A. All right. Now, having done all this, the next thing you need to do is look at this one, this group here, which is NH2. This nitrogen here will also have a splitting pattern. Are you getting it? But there's no carbon here, so it's going to show as a singlet. We can put it anywhere around here due to hydrogen, but it will not be that sharp. So it will show something that is very, because of effect of solvent, this one will not be that sharp. It shows something like this here. Let me just continue our line. All right. It's going to show something like this here. So this will be the NMRO spectrum for this compound. The carbon NMRO, nobody asked us to find it. I was just trying to see if we can actually find it. So this one is due to D. All right. You can just memorize it. That is if it will come out on top. And that is that. Thank you.